Hello everyone, and welcome back to the Natural Gas Engineering Internship at Petro. I hope all of you are doing well. My name is Rahima Babayeva, and I'm a fresh graduate from the University of Aberdeen. I have finished my Master of Science in Petroleum Engineering, and I'm going to be your moderator for today's session on behalf of Arab Oil and Gas Academy. Today's webinar is going to be about horizontal fracturing system given by Dr. Ali Daneshy. Dr. Daneshy was recognized for his many years of service to the oil and gas industry, academic institutions, and SPE, and his immense contribution to rock mechanics and hydraulic fracturing. He is a president of Daneshy Consultants. Areas of expertise include well completion and hydraulic fracturing, geomechanics, intelligent completions, ISD applications, and design and water control. He studied Bachelor of Science in Mining Engineering at University of Tehran. He also studied Master of Science in Mineral Engineering at University of Minnesota. Then he pursued his PhD in Mining Engineering at University of Missouri-Rolla. He worked as a director in petroleum engineering at the University of Houston between 2004 and 2007. He was a vice president of integrated technology products at Halliburton Energy Services in Houston, Texas between 1996 and 1998. He also worked as operation technical manager for the Europe-Africa region of Halliburton in London, England during his professional experience. Moreover, he worked as a director of European Research Center for Halliburton in Holland. Dr. Ali Daneshy has over 50 technical publications in various areas of oil and gas completions and production, and over 15 publications in various areas of technology management and engineering creativity. He is also co-editor-in-chief and publisher of Hydraulic Fracturing Journal. Now, before we start today's session, I would like to mention that you can ask your question from question and QA part, and 3 or 5 questions will be answered by Dr. Ali Daneshy. Let's welcome Dr. Daneshy. Dr. Daneshy, we are delighted to be here today. So, it's your turn.
Okay, good morning. Let me first give you a little bit history of horizontal well drilling and fracturing and what brought this entire process into the oil and gas industry. The driver for this process was the driver for this process was the shale gas reservoirs in the United States. As you see the map of the United States right now, the United States has a large number of shale gas reservoirs. And the difficulty producing these shale reservoirs was that their permeability is so low, this is in the order of nanodarcies, that drilling vertical wells and trying to fracture them did not produce sufficient production to make the operation economically feasible. So in an attempt to find ways of producing from these very, very low permeability reservoirs, people started to drill horizontal wells. As they started to drill these horizontal wells, although the production was a little bit better, still the production was not sufficient to give these reservoirs enough financial results to justify moving ahead with it. The operation was not economically feasible. So then the industry decided, why don't we also fracture these horizontal wells? And by fracturing these horizontal wells, increase their production to reach an economical level so that then we can move ahead with it. The result of all of this has been that today, United States is the largest producer of oil and gas in the world. And we are not only energy sufficient, but in fact, we have surplus in some areas too. So this has been really a game-changing technology. The results have been quite spectacular. So let's look at the critical elements of fracturing horizontal wells in low permeability reservoirs. What are some of the issues that we need to address in order to make this process successful? The issues can be divided into 2 general groups: technical understanding of the subject, and of course, the question of economics, logistics, and cost. On the technical side, the critical elements are how do we initiate and extend fractures in horizontal wells? What are the mechanics of fracture initiation and extension in horizontal wells? And as you will see, this is very difficult than in vertical wells. The next question is borehole stability. Horizontal wells are generally recognized to be less stable than vertical wells. So how do we maintain a stable borehole? Well productivity. What do we need to do in order to optimize the productivity of these fractured horizontal wells? Completion reliability. When you put a completion system in a horizontal well, which is 2 miles long, how do you make sure that this completion is reliably performing its functions? And then the diagnostics, how do we establish what we have, what has been the result of the operations, and are there areas that we need to improve in order to get better results? Then, of course, there are questions of cost economics. What is a fit for purpose completion design? What is a fit for purpose fracture design? For example, how much fluid and proppant do we need to pump into these wells in order to get good results? And how reliable are these downhole tools that we use, and how well do they perform their expected function? So let's look at reservoir objectives. What are we trying to do when we drill these horizontal wells? Many of these shale reservoirs in the United States and in other parts of the world are stratified reservoirs. As you go in depth up and down in the reservoir, the permeability of the reservoir changes. There are streaks of high permeability within low permeability streaks in the reservoir. By drilling a horizontal well and creating these fractures in it, what we do, we create an environment in which fluid flows horizontally along the reservoir into these fractures, and then along the fracture into the wellbore, and then of course we produce it. So creating these fractures in the horizontal well creates a pathway, a passage for the fluid flow to flow horizontally within the reservoir and then vertically within the fracture into the horizontal well and then to the surface. The other types of reservoirs are very heterogeneous reservoirs in which the permeability and the porosity and the reservoir fluid are distributed randomly within the reservoir. So by creating these fractures with many branches in them, which I call off-balance fractures, these are not perfectly linear fractures, off-balance fractures, we create many of these passages, many of these conduits within the reservoir, so that wherever the fluid is in the reservoir, it can flow into one of these branches of the fractures, along the fracture, into the horizontal wellbore, and then coming to the surface. So why do we want to drill horizontal well and fracture it? Here are the objectives. First, we get higher flow rate from these wellbores. More production per well allows more concentration and efficiency of operations. Consider this. We drill a horizontal well. In the United States, drilling a 2-mile long horizontal well is very common. It's done almost routinely every day. If you were going to produce a 2-mile length of the reservoir, how many vertical wells would you have had to have? And how many fractures would you have had to have in these reservoirs? By drilling a horizontal well and creating fractures along the length of that horizontal well, you get more production per well, which means more concentration and efficiency of operations. Instead of drilling 50 wells, you drill 1 well. Instead of fracturing 50 separate fractures, 100 separate fractures, you basically create fractures at one time. You set up the process, one time you go fracture 1, 2, 3, 4, 5, and so on. Lower cost per unit of production. We will have lower total drilling, completion, and fracturing operational costs. and lower total logistics, people, and facilities costs. Again, consider you want to produce a section of the reservoir which is 2 miles long. If you were going to drill 20 vertical wells, you will have to have 20 separate drilling operations, 20 separate completion operations, and you will have to mobilize your people 20 times to come and do each one of these wells. You will have to mobilize fracturing systems 20 times in order to come and fracture these wells. And so the cost of these would be much higher than if you do all of these at one time. You just drill one well and fracture it 1, 2, 3, 4, all the way from beginning to end. Earlier production, again, consider the same thing. You drill the horizontal well and you fracture it. The production that comes in is faster. You take less time to reach a commercial cumulative production from the well to make the operation financially productive. Reduction of reservoir risk. Production reflects average behavior of a much larger reservoir volume, so that basically you get an average from a large section of the reservoir, and that reduces the risk of having bad reservoir sections in one well and good reservoir sections in another well. And then HSE, health, safety, and environment friendly. You have got fewer drilling sites, less materials for drilling, less materials for fracturing, and less waste. So as a result, this operation from an environmental point of view is in fact more friendly than you would have had if you were going to drill multiple vertical wells, fracture them to get the same production result. So let's get into some of the technical conversations, technical discussions of fracturing horizontal wells. As you know, the orientation of the hydraulic fracture is perpendicular to the minimum principal stress. So if this arrow indicates the orientation of the minimum principal stress, hydraulic fractures will be perpendicular to it. So now, if you drill your horizontal well in this direction, you create axial or longitudinal fractures along the length of the well. If the horizontal well is in this direction, the fracture will be inclined with respect to the wellbore. And if your horizontal well is parallel with the least principal stress, you create fractures which are perpendicular to the wellbore. And we will evaluate each one of these separately to see what would be the consequence in each case. As we will see during this discussion, in practice, we actually try to drill the horizontal well in the direction of the minimum principal stress so that the fractures that we create are in fact perpendicular to the wellbore. But we will get into details of that as we move forward. So let's first look at how fractures initiate in a horizontal well. You see, if you have got a cylindrical borehole, as you see here, and you apply a fluid pressure inside it, the wellbore breaks along the length of it. If I was going to give you an analogy, consider a pipe. If you put pressure inside the pipe, you split the pipe along the length of it, always. That is because pressurizing the wellbore induces a tangential stress on the borehole that causes the borehole to split along the length of it. This is always the case. It is related to the shape, which is cylindrical. This is independent of the stresses. The borehole generally will split along the length of it. So if you want to initiate a transverse fracture in a horizontal well, you need to have a place in the formation in which fluid pressure can act in a different direction than perpendicular to the borehole wall. For example, if you have got a natural fracture in the formation, then fluid pressure can act on the faces of this natural fracture and create a stress in this direction, as you see, that will cause the fracture to grow in the direction perpendicular to the applied pressure. So in a horizontal well, where are the possible sites in which we can create a transverse fracture, a fracture which is perpendicular to the borehole? These locations, for example, would be if you have got a natural fracture. If you have got a natural fracture, this is the horizontal well. This is the liner or tubing that you have placed inside the horizontal well, and you have isolated a section of this horizontal well with these packers. So if you have got a natural fracture in the horizontal well, application of fluid pressure on the walls of on the faces of the natural fracture can cause the fracture to grow perpendicular to it, as you see here. Or if the natural fracture is at an angle, it will cause the natural fracture to extend along its length initially. Another place you can initiate a transverse fracture will be at the packer, because the fluid pressure acting on the face of the packer induces a stress along the packer and perpendicular to the packer face that will cause a fracture to grow, as you see in the picture. Or if, for example, you're applying fluid pressure at the bottom of the well is a place in which you can create a hydraulic fracture perpendicular to it. Of course, you realize a horizontal well has only one bottom. So you can create, if you apply fluid pressure in the horizontal well at the beginning, you could create fracture at the end of it. But if you want to create more fractures in here, you will have to go and isolate segments of it with these packers and then apply fluid pressure on the backside here to create the the transverse fractures that you desire to create. This is an actual view of a horizontal well. This is actually the bottom of the well. This is water sitting at the bottom of the horizontal well. You see here these natural fractures. You see there are quite a few natural fractures along the length of this horizontal well. This is the horizontal well. You see the natural fractures. And when you apply fluid pressure inside this horizontal well, depending on which of these natural fractures is larger and more favorably oriented, it will initiate the first hydraulic fracture from it. But you also can see that because we have got so many of these natural fractures in the horizontal well, we don't really know where the horizontal well will initiate along the length of the where the hydraulic fracture will initiate along the length of the horizontal well. You will have a random fracture location if we just go depending on the natural fractures to direct the hydraulic fractures. So if the hydraulic fracture is going to initiate from natural fractures, we will have random and unpredictable fracture size and location. We don't really know exactly where along the horizontal well these fractures are located, depending on where the natural fractures are. The other thing is that since we are depending on random location of natural fractures, we have a random location of hydraulic fractures, and this will interfere with orderly production and reservoir depletion. We want to produce the reservoir in an orderly manner so that the entire reservoir is produced, not just a segment of it. It creates possibility of multiple fractures randomly located inside the wellbore. Where these natural fractures are, that's where the hydraulic fractures will be, and that does not give us possibility of controlling the production, and there is possibility of production interference between fractures which are closely spaced together. And then, of course, you will have random and unpredictable fluid and proppant distribution among the multiple fractures. What I'm trying to say is that when you go to fracturing the horizontal well, we need to have a system by which we can control the location, the size, and the conductivity of the fractures. If we depend on natural mechanisms to control the process, we will end up with an unpredictable and an inefficient outcome. And as you will see, as we move on, you will see the systems that are being used for this purpose by the industry. So the issues which are related to fracture initiation at the packers, if the fractures are going to initiate at the packers, you don't know where the fracture is. Is it on this? You have isolated this segment of the wellbore. Is the fracture going to be on this side of, for example, the previous segment? When you fractured this segment, you created a fracture here. When you come to create a fracture here, are you going to create a fracture on this side of the packer or this side of the packer? Ideally, what you would like to have is a fracture which is equally spaced. You don't want to create a fracture on this side of this packer and then next on the other side of the same packer. These two fractures will be very close to each other, and only one of them will contribute to production. Effect of wellbore orientation is wellbore. If we place the wellbore parallel with the least principal stress, the hydraulic fractures will be perpendicular to the wellbore orientation. The advantages are that we can create multiple hydraulic fractures to get better production from this. As we will see, there are several commercial completion systems available in the industry to allow us to get this outcome. And in fact, that's the reason this is the most common way of drilling and fracturing these horizontal wells. The most common way is to drill the well parallel with the least principal stress and create transverse fractures perpendicular to it. And as it turns out, if the wellbore is directed along the direction of the minimum principal stress, that borehole is most stable. It is less likely to give us stability problems. The things that we need to also be careful about is, if we are going to do this, we need to have, in order to get these separate fractures, we need to have short perforated intervals. The way we create these fractures is to perforate the well here, perforate the well here, perforate the well here, and perforate the well here. In order to get these results, the perforated interval, for example, here in this location, needs to be very short. In practice, this is something like 1 to 2 feet of perforated interval. I will show you how this is done in actual practice. We need to have sufficient spacing between these fractures so that they do not interfere with each other. In other words, sufficient spacing between perforated intervals so that the induced fractures stay separate and do not join and interfere with each other. So now what happens if the wellbore is inclined with respect to the minimum principal stress? In this case, the minimum principal stress is, as you see, is horizontal on this slide. And if the wellbore is inclined with respect to that, this is the most likely situation if we do not know the orientation of the minimum principal stress and we just go ahead and drill a well. This is more likely the outcome of that. The chances of the wellbore being exactly parallel with the minimum principal stress is very low. The wellbore will be at an angle, and we create these fractures as you see here. Again, in order for us to create separate fractures, we need to have very short perforated intervals. We need to have fractures which are reasonably separated from each other. And I'm sure you realize that now the separation between these fractures is not the separation at the wellbore, it is the real separation perpendicular to the fracture face. The other thing is that when you create fractures in this fashion, your fractures have got many branches. And these branches, the consequences of these branches is that it actually reduces the spacing between these fractures and interferes with the planned production scheme that you had in mind. As I will show you in just a little bit, this type of fracturing is more likely to cause screen out. And with the screen out, what I mean is that the proppant gets trapped inside the fracture and you cannot pump into the fracture anymore. The pressure gets too high and you have to abort the job. So inclined fracture is likely to start as longitudinal or axial along the length of the fracture and then reorient itself to become normal to the least principal stress. Fracture will have many branches and rough surface. Proper movement is mostly controlled by fracture roughness. And you also will have, as I will show you in just a little bit, high initiation and early extension pressures during your fracturing treatment. Let me show you some example laboratory tests to show you what can happen. These are rectangular blocks. I actually performed these experiments myself. These are rectangular blocks of rock. And what we do in each of these, on each face of this, we apply a different principal stress. So perpendicular to this face, the stress in this case was 300 psi. Perpendicular in the vertical direction, it was 1300 psi. And perpendicular to this face of the fracture was 1200 psi. So the least principal stress is 300 psi. The wellbore that you see in the background, this is the wellbore in this example. And what the face that you see here is the fracture face that was created in this experiment. You see that the fracture extended along the length of the horizontal well. But once it got away from the wellbore, you see it's perpendicular to the minimum principal stress. It is turning to become perpendicular to the minimum principal stress. This is another example. And if you look at the face of this fracture, for example, or the face of this fracture, you see that it has got a rough face and it has got branches. In this example, the stress in the vertical direction was 1000 psi, perpendicular to that fracture face was 500 psi, and perpendicular to the front of the fracture that you see, it was 1200 psi. Minimum principal stress is 500 psi, and you can see that inside it, as the fracture is growing, it is trying to become perpendicular to this face. This example is showing an extreme case. The minimum principal stress in this case is in the vertical direction, 200 psi, 800 psi on that side of the fracture, 1300 psi on this face of the fracture. The minimum principal stress is 200 psi. The wellbore is running like this in that direction. You see the fracture initiated along the length of the wellbore, but is turning. It's turning to become perpendicular to the minimum principal stress. So regardless of which way the fracture is, which way the wellbore is oriented, the fracture that you create after a short time will reorient itself to become perpendicular to minimum principal stress. This is an extreme case. Again, vertical stress in this case was 200 psi. On this face of the fracture, the sample, the pressure was 1500 psi. On perpendicular to this face, to a screen face, it was 2000 psi. Minimum principal stress is 200 psi. You see the wellbore here. There is the wellbore. You see the fracture is turning here, but it turns suddenly or sharply here to become perpendicular to the minimum principal stress. So basically, it is very important to recognize that the fractures that we create in horizontal wells, after a short time, they reorient themselves to become perpendicular to the minimum principal stress. Let me show you a very interesting picture and an extreme example. It's going to take you a while to grasp what the picture is showing. This is the horizontal wellbore. It is perpendicular to this face that you are seeing. The stresses on this sample, these are the two faces of the sample. They were together, and now they're separated, opened up, so you can see what you are seeing. If you look at my picture, and I'm showing it with my hands, the fracture was like that, and it has been opened, so you are seeing the two faces of it. This is one face, and this is the other face. This is the wellbore. You see, the wellbore has got an axial fracture along the length of it. and then a fracture perpendicular to it. And you see how the axial fracture turned around to become perpendicular to the borehole axis. The stresses were 2000 psi in this direction, 2500 psi in this direction, and perpendicular to the fracture face, it was 300 psi. So the fracture initiated a smaller stress between these two, 2000, 2500. The fracture initiated axially perpendicular to that stress, which is 2000 psi. Once it extended a short distance away from the wellbore, it reoriented itself to become perpendicular to the minimum principal stress, which was just 300 psi. But you can also see branches of the fracture. You see branches of the fracture here. And you can see that the reorientation was gradual, but you have got sharp angles between the axial and the transverse fracture in this sample. This gives you a picture of how a fracture can reorient itself within the formation. I'm going to give you a little bit more time to recognize what you're seeing. The sample was like this. It is opened up, so you are seeing the face of the two faces of the fracture along the transverse fracture, and you can see the axial fracture, which is running along the length of the borehole. This was the length of the axial fracture, and of course, it is extending into this sample. So how does the fracture reorient itself in the horizontal well? The fracture reorientation may occur in multiple locations. The fracture reorientation, you create an axial fracture, and then it reorients itself, and it may occur in multiple locations depending on formation heterogeneity. And since the tendency of the fracture is to grow in a single plane, this creates shear fractures during the reorientation process. Along the way, you create a bunch of shear fractures along the length of it. You see the fracture is basically confined within the two packers in this particular example. The orientation is perpendicular to the minimum principal stress once it gets away from the borehole influence. Once it gets away from the borehole, it's perpendicular to the minimum principal stress. So, effect of wellbore on horizontal well fracturing. If the wellbore is perpendicular to the minimum principal stress, you create fractures which run along the length of the wellbore. The advantage of it, this system is easy to fracture, and you can create these fractures at a lower pressure. Interference between the fractures is not a big issue because they're basically in the same direction. And majority of the horizontal fractures initiate longitudinally along the axis. The things to consider is that there are very few examples of this reported by the industry. And the reason is because you do not get as much production from this system as you would if the fractures were perpendicular to it. And if you want to create multiple fractures in the horizontal well, then you need to have large spacing between these fractures. This is basically not being practiced. I'm just showing you what would hypothetically happen if you try this. In case wells, transverse fractures have to initiate at perforations. In such cases, the perforated interval should be kept to just a few inches. Now, hydrojet perforation is better than shape charge perforations because it creates a larger hole. Hydrojet perforation, by that what I mean is when you inject an abrasive material perpendicular to the borehole, and by abrasion, you create a hole in the formation. The hole that you create in the casing and in the formation will be larger than if you use shape charges and you just fire the bullet into the face of the wellbore. So let's look at effect of perforation patterns. If you put the perforations in one plane, then you create the best environment to create a single transverse fracture. If you spread the perforations, as I'm showing here, in a helix, one here, one here, one here, one here, here, then the initial fracture initiates axially along the length of the wellbore, and then, as I will show you in a little bit, it reorients itself to become perpendicular to the minimum principal stress. And of course, if you could create this, this will be the best pattern, the easiest to fracture the formation, if you could do this. As it turns out, in practice, it is not possible to put all of these perforations in one plane. And the mechanical equipment that we have creates perforations, as you see, in a spiral around the borehole, but we can keep this distance very short. In practice, this distance can be as short as 1.5 to 2 feet. In some applications, this can be just 1 foot long, which gets us close to this particular ideal situation. So if the initial fracture is axial and it reorients itself to become perpendicular to the minimum principal stress, then this can jeopardize the final execution by several things. First, it is possible for this transverse fracture not to intersect the wellbore where the perforations are located. In other words, the perforations could be here and the fracture reorients itself here. What that does is that in order for the proppant to enter this fracture, it has to go through these axial fractures, move along the axial fracture to get into this. And in that case, then this narrow transverse, narrow axial fracture may trap the proppant and screen out very early. It may trap the proppant and just block the movement of fluid along the length of the axial fracture to get into this transverse fracture. And the industry's answer to that has been to try to use very small size proppants so that the chances of them getting stuck is low. And the other thing is you increase the volume of fluid that you pump at the beginning without any proppant in order to create and erode a channel in this axial fracture to make it wider, to make it possible for proppant to enter this fracture later. But the effect of this will be that the fluid pressure at the beginning of the treatment will be relatively high. And as the fracture reorients itself, then the pressure drops and makes it possible to complete the job at a reasonable rate. This is an example case history. You're looking at pressure in PSI on this axis and in blue color. This is the fluid pressure during the early times. The pink color is showing the injection rate, and you see the scale on this axis. So, for example, at the beginning of this particular treatment, fluid was injected for about almost 3 hours at rates of less than 5 barrels per minute. And the reason the rate is kept so low is because the pressure is so high. You cannot inject the fluid at more than that pressure. That's the limitation of the borehole. And you see, as the fracture erodes and opens a wider channel, gradually we are beginning to increase the injection rate. And as the pressure drops, we are able to increase the injection rate such that at the end of this fracturing treatment, we were able to complete the treatment at 45 barrels per minute at a lower pressure than we started with. What caused this difficulty at the beginning of this was the fact that the fracture initiated axially and required much higher pressure for its extension, and the fracture was very narrow, required a high pressure for its extension. So this fracture, for example, took nearly 7 hours to complete. And of course, we don't want this to happen. I'm showing you an example of an extreme case when axial fracture initiation can interfere with the operations that we want to do. This is the reason why we try to create an environment as suitable for the fracture to initiate perpendicular to the borehole. So fracture extension in open holes offer a much better connection between the wellbore and the fracture because there is no perforation and there is no limitation to fluid and proppant movement into the transverse fracture that you have created. There's no limitation caused by the number of perforations, their size, or some perforations not being directly connected to the fracture. Pressure inside the wellbore promotes propagation of an axial fracture along the wellbore, and then it will reorient itself to become transverse fracture. And the transverse fracture, of course, is what causes the production, gives us the production that we need. On the positive side, open hole itself and axial fracture also contribute to production during the early times. But because of the random natural fracture distribution, there is very little control on how many fractures we create and where they are located. And this is the reason this type open hole fracturing, which started at the beginning, is not practiced very often anymore because you really don't have much control over the fracturing process. And also because we have learned how to create transverse fractures from cemented liner completions. In cemented liner completions, the most desirable situation is to have perforations which are perpendicular to the borehole. This is the least desirable when you perforate along the axis of the borehole. We try to generally put them in a helix around it and keep this perforated interval as short as possible. So fractures that we create from open hole, these are the features of it. Advantages: lower cost, production contribution from the wellbore as well as the fractures. The completions are much faster. You can drill the well and fracture it much quicker. Better connection between the wellbore and fracture. You have much less likelihood of screen out, and presence of axial and transverse fractures can give better early production. The disadvantages: you have less control on fracture location. You have higher expected initiation and early extension pressures. Less flexibility if you are having operational problems. Larger area for proppant flowback. The proppant flowback can get into the horizontal open hole, and because you have got better connection between fracture and the wellbore, you can have larger volume of proppant coming back into the hole. It's more difficult to clean up returned proppant if you get it. You have got the probability of fracture crossing the packers to the other system, and it's more difficult to refrac at a later date. Nevertheless, let's look at the options that you have for fracturing open holes. Here is a completion system. You have got a liner in the well, and the liner is segmented by these open hole packers. So you have a wellbore which has been segmented by these packers into multiple intervals between these packers. Inside the borehole, you have got these sliding sleeves, and at the end of each sliding sleeve, you have got something like a funnel. And the opening of this funnel, the hole at the end of the funnel, gets bigger as you move towards the wellbore, towards the head of the well. So this is the toe of the well, this is the heel of the well. So the way you fracture this is this system is installed. You drop this first ball inside the hole. The ball goes through these holes in the previous one, and it seats on the funnel sleeve, in which it is smaller than the size of the ball. When it seats there, the fluid pressure causes this sleeve to slide, and when this sleeve slides, it exposes these perforations which are in the liner itself. And when these perforations are exposed, the fluid pressure creates a fracture here. Then once this fracture is done, you drop the next ball. The next ball goes through these larger holes seats in this sleeve here. When it seats here, the fluid pressure pushes this sleeve open, exposes these perforations, and you fracture this interval. As soon as this is finished, you drop the next ball, which is this ball. It comes in here, closes this sleeve, pushes it open, you fracture this, and the same thing, you go on all the way to the end. The advantages of this system is it's a simple completion. The fracturing operation is continuous. You just drop a ball at the end of each stage and just move on. It's a lower cost. At the beginning of this, it was very frequently used in US and Canada. And of course, it's suitable for large applications. The problems with this system is if you are having any problem with your fracturing operations, you have limited options for troubleshooting. And you have very limited options for cleaning the wellbore and proppant if it falls into the hole. The hydraulics is quite complicated, and you have got potential for proppant blockage inside the wellbore itself. The proppant can flow back and accumulate inside the wellbore and cause problems. This was a popular system at the beginning of horizontal well fracturing. It is not being practiced very often anymore. These are the return balls that have come from it. You can see the size increases as you go from one to the next stage, as you see here. You see the ring here. This is where the ball was seated inside the liner. And this is basically shows these are the balls which have, after the fracture job is finished, when you open the well to flow it back, the balls come back and you recover them at the surface. A successful application of these in the Bakken Formation, the fracturing fluid was a cross-linked gel. The well was fractured in 10 stages. The spacing between these ports were anywhere from 400 to 700 feet. The packer spacing was from anywhere from 350 to 700 feet. And the maximum proppant concentration that was reached in this treatment was 12 pounds per gallon. This is the fracturing treatment. Again, the pressure is shown on this axis in dark blue color. Rate is shown on this axis in purple color. This is one stage of fracturing. A ball was dropped, the next stage of fracturing, a ball was dropped, the next stage, ball was dropped, the next stage, the next stage, the next stage. You can see that in a matter of something like 4 hours, they were able to create 6 frac stages. This is the rest of it. Again, the created fractures. If you look at the pressure, you see high pressure, which drops rapidly. This is when the fracture initiates axially and reorients to become transverse. That's what causes this pressure drop. You can see it happens at the beginning of each stage. But in a matter of 8 hours, the well was fractured in 10 stages, and low cost and effective fracturing, no problem. The next system that was tried in horizontal open holes was a system which is called plug and perfractory. Once again, the liner is segmented by these packers. You put the liner inside the hole and set these packers. So which divides the horizontal well into multiple segments between these packers. Then we go inside this horizontal well, inside the well, and we set packers inside of the hole, inside of the liner, perforate inside the liner and create a fracture. Then after this is finished, you go inside the well, set the next plug, perforate the well, create the next fracture. The next plug, perforate the next fracture, and so on. And once we are done with all the frac jobs, then we go inside the wellbore and mill out these bridge plugs, from the wellbore, and you put the well on production. The advantage of this system is that since you mill out the completion, if you have a screen out, all you have to do is go circulate the fluid out of the well and continue with your operations, because you have full bore access inside the wellbore. You set this plug, even if you screen out, you go clean the well. Then after the well is cleaned, you set the next plug for the next fracturing job. The disadvantage, the cost, multiple operations to set these plugs one after the other. You need to have coil tubing or something to do that. You need to have workover tools for extended reach, and of course, delayed production, because this job takes much longer to perform than the previous one I showed you. Another system, open hole sliding sleeve with plus plug and perf, open hole divided into many using open hole packers, standard ball activated sliding sleeves, slotting from the end of it, and plug and perf in the remaining front intervals. In other words, you use two different completion systems. You use the ball activated system in the second half of the well, and you use sliding sleeves in the first half of the well. This gives you the possibility of taking advantage of both systems and creating more fractures in the horizontal well, which we have found out from experience is the proper way to fracture these wells. Another system which is being used in these wells is by hydrojetting. You go inside the well with coil tubing, perforate the, you go with the coil tubing, you set a plug inside the well by hydrojetting through the nozzle in the coil tubing, you perforate the horizontal well and you create a fracture in it. Once you can create the fracture by injecting either through the annulus or through the coil tubing, and you fracture the well. After the well is completed, you release the packer, move uphold above the fracture that you created. You set the packer again, you hydrojet the wellbore, and you create the fracture in the next stage. Here is the schematically shows you how you do it. You go with the coil tubing, you perforate the hydrojet hole inside the formation, you create a fracture in here. And as I said, there are two commercial systems available, one in which you inject the frac fluid through the annulus between the coil tubing and the wellbore. In other words, you perforate through the annulus here, or you can you perforate by pumping through the coil tubing. After the perforation is done, you can either create the fracture by pumping through the annulus between the coil tubing and the wellbore, pumping through here, or you can create the fracture by pumping through the coil tubing itself. If you are creating the fracture by pumping through the coil tubing itself, you maintain a very low injection through the annulus to basically prevent the fluid from coming back in here. And slurry is pumped either through the annulus or through the coil tubing. System can be used in both open hole and case holes. This system, you perforate, you create your fractures, and then move on. Coil tubing, you move on and create more fractures. These nozzles, you can bunch these nozzles very close to each other to create perforations or hydrojet perforations which are close to each other. So let's talk about cased hole completions. In cased hole completions, you are cementing the cased hole. The casing is cemented inside the wellbore. The advantages of this system are you have got a stable wellbore, is cemented wellbore. You have better control on location of the fractures. That's where you put your perforations. Better control on number of fractures. That's depending on how many clusters of perforations you create. Larger number of fractures are possible. To give you an example of this, today we create some of these horizontal wells, we create 200-300 fractures. These fractures are something like 20 to 30 feet separated. If you consider a horizontal well which is 10,000 feet and the fractures are 30 feet apart, you can create 300 fractures in these wells. Axial fracturing at initiation is less intensive because the perforated interval, we have learned how to put them, the perforated interval, keep it very short. Existing completion systems are more mature because they are used very often, and you can refracture these wells. The disadvantages are it takes longer to complete these operations. So your production starts a little bit later, maybe a few weeks. There is no production contribution from the wellbore itself. Everything has to come through the fractures. The connection between the wellbore and fractures is not as conductive, as robust as it was with open hole completions. The perforation strategy is very critical. You need to put these perforations very close to each other. And you have higher frequency of screen out in the wellbore itself. And of course, if it happens, then you have got the option going there and cleaning the sand out of the well and continuing with your operations. It just delays the operations. And you have got proper distribution between the various fractures, which are more complex and more unpredictable. And as I showed you earlier, what you do is you initiate an axial fracture from the perforated interval. That axial fracture reorients itself to become perpendicular to the minimum principal stress, which in practice we have learned to make them perpendicular to the wellbore itself by placing the wellbore parallel with the minimum principal stress. We make sure that the hydraulic fracture is nearly perpendicular to the wellbore. And this, as I discussed earlier, can cause operational problems. But keep in mind, since we create multiple perforated intervals within each isolated segment, we don't create a single fracture during each pumping stage. We create multiple fractures, so that even if one of them screens out, the remaining fractures in that interval will continue to grow. So what is established important here is that we establish a low pressure connection between the fracture and the wellbore. And we do that by injecting at a lower rate and until pressure drops to a reasonable amount. And then once we reach a lower pressure, then we can gradually increase the injection rate to be able to complete the job. And the reorientation of the fracture, as I discussed earlier, it creates a poor connection between the main fracture and the perforations because the fracture has to reorient itself. And this complicated fluid and proppant path may cause screen out if the proppant gets trapped inside these fractures. Now, the other thing that happens if that situation happens, and is that when we create if we create multiple multiple axial fractures, as the fracture initiates axially, it opens up. And when it opens up, since let's say that the fracture opens up something like a tenth of an inch. If the fracture opens up a tenth of an inch, the casing cannot stretch a tenth of an inch in that direction. So what happens is that the casing separates from the formation. The formation moves a tenth of an inch, but the casing does not. So that creates a gap in here. And when you create a gap in here, now that allows the fluid to enter. The perforations move along the gap. Fluid enters into the perforation, moves along the gap, and then enters the, let me move it up. Anyway, the proppant moves up into the fractures. Majority of the fractures initiate as axial, and the evidence that we have in these situations is that the planned number of fractures is less than the planned number. So what we actually do in these cases, we use a system which is called the limited entry treatment. In limited entry treatment, we limit the number of perforations such that the perforation friction pressure which is created is high enough that it causes breakdown of the all of them. Let me give you the numbers so you can appreciate it. Let's say that we inject the fluid at, say, the plan is to inject the fluid at 100 barrels per minute. If you put 100 barrels per minute, if you put 20 perforations, clusters of 20 perforations, let's say in 4 clusters, in 5 clusters, we put 5 clusters of perforations, 4 in each. If you pump the fluid at 100 barrels per minute, per perforation, the injection rate will be 5 barrels per minute. At 5 barrels per minute, you create a high perforation friction pressure. Now, here's what happens. If all perforations do not take fluid, then the injection rate per perforation becomes higher. As the injection rate per perforation becomes higher, you increase the chances of formation breakdown at more perforations. So the setup is very similar to open hole cases. You put multiple perforation clusters are created in above each plug within the horizontal segment, within that segment of the wellbore. Plugs are usually made of composite material, so you can mill it later. And after completion of all stages, plugs are milled out and the well is cleaned out. So here is the discussion of limited entry. The number of perforations, let's say that you have got this is the interval that you want to fracture. You put, say, in this example, 3 clusters of perforations. If we limit the number of perforations in each of these clusters such that the total number of perforations is limited, as we inject fluid into these perforations, the pressure goes up. As the pressure goes up, the chances of breaking down the formation at each perforation increases. So in practice, what happens is that we begin to inject fluid at a given rate based on the pressure. And as gradually the job progresses, the injection rate opens up these fractures and causes the breakdown of more perforations. And the effect of it is that we create maybe not exactly, say, as many fractures as we were planning, but we will create more than one fracture in each interval. In practice, for example, they would put 6, 7 clusters of perforations. In practice, it is possible that instead of creating 7 fractures, we create 5 fractures, but we still have multiple fractures in that interval. The advantage is lower cost. During each injection and each completion stage, we create multiple fractures. The disadvantage is that we are not exactly sure that we created a fracture at each of the perforated intervals. This is an example of this case. This is the early time. You can see that injection rate is gradually increased, and the fluid pressure here reached 2,500 psi. In this example, there were 5 perforation clusters, 24 total perforations. The fluid was injected at the end, fluid was injected at 40 barrels per minute. So it was almost 1.5 barrels per minute per perforation. And at that injection rate, the perforation friction pressure was sufficiently high. You see that to initiate more fractures, you can see that this pressure decline is indicating the fracture reorientation, which was initially axial and reoriented itself. And at the end of the treatment, all fractures are not taking fluid. And the reason you know that you are not taking fluid is the high pressure difference between the end of the job and the shut-in pressure. You have about 900 psi, which is more than what you expect to get. But nevertheless, we were able to create multiple fractures in this interval. And by creating multiple fractures, we increase the production potential of this well. This is another example of this. Again, fluid pressure in this injection was around 4,000 psi. you can see that at the beginning, the injection rate was gradually increased. The injection rate was gradually increased until about, say, 15 barrels per minute. You read it here. The brown color shows the proppant concentration. And in this case, 5 balls were at each perforation, and 12 perforations per cluster. The total number of perforations was 60. The fluid was injected at nearly 70 barrels per minute, which created an injection rate of more than a barrel per minute per perforation. At the end of this job, we did not create as many fractures as we expected. And the reason we know that is the high pressure difference between the end of the treatment and the shut-in pressure. But nevertheless, we created multiple fractures, which will increase the production potential of the fracture. So much for how the techniques that are being used. Now, this is a preliminary discussion. Keep in mind, what we are doing in practice today is more complex and more exotic than what you see here. But this was just to introduce you to the process. So the kinds of fluid that we use for these fracturing operations, what we call light cross-link gel, which means we use low concentration of a cross-link material, say gelling agents at 15, 20 pounds of gel per 1,000 barrel of fluid, and to carry the proppant in the wellbore at relatively low rate, you need lower hydraulic horsepower requirements because your fluid is not very viscous, and you of course need to have a breaker in order to break the gel after you're done with it. The most common system which is being used is what we call slick water. Slick water is water plus a friction reducer, and the advantage of it is that it is lower cost, and because you're not using a polymer, which adds to the cost, of course, the higher rates are possible because you're just injecting water. And today we are coming up with very exotic the slick water friction reducers that make the fluid a little bit more viscous, so that the water with friction reducer behaves more like a gel fluid. Foams are used sometimes if there is CO2 available, but these are relatively more expensive, of course. And nitrogen is sometimes used, and nitrogen is converted from liquid to gas, and in some of these wells is used with no proppant, you just pump nitrogen to create the fractures. The proppants which are used in these, we use finer size proppants. The reason we use finer size proppants, as I discussed earlier, is to make it easier to carry the proppant inside the axial fractures before they enter into the transverse fracture. 100 mesh sand is being used. And nowadays, we even use some nano proppants, which are finer, smaller in size than 100 mesh. 4070 mesh sand is being used, not very often. 2040 mesh sand is used, not very often. And when these are used, it is close to the end of the job. Common concentrations which are used in these for gas wells, 30 to 60 kilogram per cubic meter at the start of the job, and 60 to 250 kilogram per cubic meter in the middle or end of the job. Common concentrations for oil wells would be higher, 1,200 to 1,400 kilogram per cubic meter. Sometimes in deeper wells, we use higher strength proppants, which would be synthetic proppants, man-made proppants. Resin-coated proppant is often used to keep the proppant trapped inside the fracture. The resin joins the proppant particles together and prevents it from coming back. Lightweight proppants are used to carry the proppant deeper inside some of these fractures. And to show you the different types of proppants, this is Ottawa sand. You see round size particles. This is regular sand. Lightweight proppant. This is synthetic proppant. This is low density proppant, which is again synthetic proppant, the man-made proppant. Brown frac sand is a lower quality sand. This is resin-coated sand. The brownish color is the resin. And once the resin sets, of course, it attaches the proppant particles to each other, which makes it more difficult for the proppant to flow back. Sintered bauxite is being used. This is used not very often because it's more expensive and, of course, it is heavier. But it could be used, not very often these days. And low-density proppants used mostly help to carry the proppant deeper inside the fracture. It's not as conductive as regular proppant. That may not be a handicap for low permeability reservoirs. Used in very low concentrations to create partial monolayer distribution inside the fractures. And of course, they are not mechanically as strong as regular proppant. And this, I'm showing you the lightweight proppant. This is 162 grams of Ottawa sand in a cylinder. You can see the height of the sand here. This is regular sand. Lightweight sand, because it's lighter weight, carries more volume, occupies more volume. All right, that's the end of my presentation. Now I'll be very happy to answer questions that people may have.
Thank you so much for this extremely insightful and informative session. We are very grateful that you took the time out of your busy schedule to address our group. Now I would like to pursue with a question of our audience. Okay, I'm starting, okay? The first question is, what are the harmful chemicals in hydraulic fracturing flowback waters?
Yeah, I didn't hear that. Can you repeat that, please, again?
Of course. What are the harmful chemicals in hydraulic fracturing flowback waters?
Oh, the harmful chemicals that people are talking about would be these gelling agents, for example, that we use for that, and the friction reducers. These are, people talk about these as being harmful, but they really are not. It's harmful chemicals could be if we use a biocide, something to kill the bacteria in the water. Those could be harmful. But other than that, the gelling agents that we use, you know, these gelling agents that we use, you'll be interested. You eat them in your ice cream. And friction reducer that is used, these are polymer fluids. They degrade, and we usually add chemicals to break them also, to basically degrade them and reduce to bring them back. So harmful chemicals that are used are not many, as I said. The only harmful chemicals are biocides and bactericides, and we use those in order to make, you see, the gelling agents that we use are killed by bacteria. And so we sometimes add bactericide to the fluid to kill the bacteria so that they do not degrade the gelling agents.
Thank you very much. How we can prevent fracture to propagate water zone, which is below of oil zone?
Okay, that's a very interesting question. Thank you for that question. You see, it keeps several things in mind. These horizontal wells that we fracture, these are usually very deep. For example, in the United States, majority of these wells are at depths of 10,000 feet. The water that we use for irrigation and for other things, these waters are located at depths of less than 1,000 feet. So the water that is contacted by these fractures is very deep water, and these are usually saline waters, have got high salinity. So these are not suitable to be used for daily applications like agriculture or drinking or anything like that. So these fractures generally do not propagate so high. They don't move up so high, 10,000. Can you imagine if a fracture moves 10,000 feet up, that it will not be suitable for production of these reservoirs? When you drill these wells and you get good production rates that we are getting, it's indicating that the fracture is propagating within the reservoir and not too high up. If the fracture moves up, say 3,000-4,000 feet, the volume is not enough to make the fracture go more than the 100 or 200 feet horizontally within the reservoir, and that well will not be productive enough to justify drilling and completing it in order to get the production from it. So people don't realize that the water which is contacted by these fractures, first of all, is saline water, which is not suitable for most of our applications. And second, it is it's very deep. Even if the fracture breaks into that water zone, that water is so deep that that's not the kind of water that we'll be using. And that water will be usually as deep as the reservoir that we're trying to produce.
Thank you very much. And another question is, what dictates the direction of the fracture? Can it be controlled by the operator, or it's mainly controlled by the distribution of the stress?
It is controlled by distribution of the stress. We have very little control on which way the fracture goes.
Thank you very much. Another question is, what makes the nozzles to be very closely bunched together?
What makes what, please?
What makes the nozzles?
Yeah.
To be very closely bunched together.
Oh, the nozzles are, if you're, okay, let's talk about the nozzle that we talk about is when we use an abrasive material to create the perforations. And that abrasive material usually is already, the nozzle is already located, placed on the coil tubing, is built into the coil tubing. So when you have the nozzles, you basically put them in wherever you want to put them. You can, usually we may put 3 nozzles along the horizontal, along the coil tubing to create 3 hydrojet perforations inside the well. You can put 4 of them if you want, but it's, in theory, you can put more of them. In practice, we usually often just put 2 of them, one on top and one at the bottom of the nozzle to perforate to the top and to the bottom. But if you want, you can put 3 of them also. But that is, in nozzle, it is man-made. In the case of perforations by bullets, by shape charges, that again is also built into the completion system. You have got a piece of pipe which has got these bullets already built into it, and then when you fire the bullets, it goes shoots right where it was located. You build that section at the surface. It is built at the surface, put inside of the tubing or liner or whatever you have, push down the hole, and then it is fired from the surface. You fire it from the surface, it shoots and creates the perforations.
Thank you very much. The final question is, how can we control water in horizontal wells?
How can we control what?
Water.
Oh, the water, you cannot control the water. When you go to produce the well, whatever the hydraulic fracture has contacted, is what flows into the well. If you contact, for example, gas and water, the produced fluid will be gas and water. If the reservoir is in oil and gas, the produced fluid will be a mix of oil and gas. Whatever the reservoir produced is what comes out of the well.
Thank you very much. Thanks a lot for answering our question with a special attention. We hope we shall see you in our next sessions as well. Also, please do not forget to finish and submit the quiz before deadline. Moreover, you can watch this webinar again from PyroPetro's YouTube channel. Stay safe, everyone.
Just a second. Please, sure. Thank you very much for the invitation. I enjoyed this. Thank you very much. And if any of your audience have got questions that they like to ask, I'll be happy that they can send me an email, and depending on how many of these I get, I'll be happy to answer them as I can. But thank you for the invitation. Ahmad, thank you very much for considering me for this, and I enjoyed this. And everybody, wherever you are, have a good day.
Thank you very much, Dr. Ali Daneshy. Thank you very much. We appreciate it. Thank you.